Dear students, today we will study speed of longitudinal wave. Here we are taking the case of sound wave. We know that in longitudinal wave, elements of medium oscillates forward and backward along the direction of wave propagation. Also in this case, the sound wave travels in form of compression and rarefaction of small volume elements. That may be air particles if we are taking a long tube filled with the air for the propagation of the longitudinal wave. Now here we'll discuss a property concerned with the longitudinal wave and the medium through which they are propagating, bulk modulus. So first we will understand what is the bulk modulus. It is the property of medium which determines to what extent the volume of a medium particle changes with respect to the change in pressure on it, means on the particle. Say if we express the bulk modulus by capital B, then its value will be given by ratio of change in the pressure with respect to change in volume. Say this is the equation number 1. Considering this equation number 1, here in this equation B will be known as bulk modulus, delta P will be known as change in pressure, and delta V upon V will be known as fractional change in volume, which is due to the change in pressure. Since the density of medium, say expressed by rho, changes at each position as a longitudinal wave, propagates, we would have to involve here the rho, means the density of the medium. If we take here the dimension of bulk modulus and the density, then the dimension of ratio of bulk modulus and the density, dimension of ratio B upon rho will be given by here m to the power 1, L to the power minus 1, T to the power minus 2 divided by m to the power 1, L to the power minus 3 to the power minus 3, T to the power 0. So again it equals L to the power 2 and T to the power minus 2. With the above ratio of dimension, with the above dimension, we can get the velocity of the sound wave equals to square root of bulk modulus divided by the density of the medium. So we can mention it the equation number 2. Thus, we see the speed of propagation of wave in fluid depends on bulk modulus, density of the fluid. Now if we consider the case of longitudinal wave through a solid medium, longitudinal wave through a solid medium. In case of solid bars, we are taking here the bars which are solid and have some length. In case of solid bars, the resultant modulus of elasticity is given by Young modulus. It is so because the linear expansion of the bar is prominent here comparatively to its volume expansion. So here the Young modulus is concerned with the linear expansion of the solid bar. For a longitudinal wave in a solid bar, the velocity of wave will be given by V equals to square root of Young modulus divided by the density of solid bar. Here we can mention that Y is the and the rho here is the density of solid bar. Now one thing is to remember here that although density of solid and liquid are comparatively higher, than the gases, but speed of sound greater in solid and liquids. Than the gases. This is due to the fact that solid and liquids are less compressible than gases, which means that they have greater bulk modulus, greater value. So if we talk here, the velocity of wave, the longitudinal wave, in gases for an ideal gas, the relation between pressure P and volume V is given by equals to n kBT, where n is the number of molecules in volume V. Kb is the Boltzmann constant, and the capital T is the temperature of gas in Kelvin. Which is in Kelvin. For an isothermal change in the gas, we can write here B delta P plus P delta V equals to 0. And from the same relation we get P equals to minus delta P divided by fractional change in volume. Say this is equation number 3. So now here from equation 1 and 3, we can get the expression for speed of longitudinal wave in ideal gas, which will be equals to V equals to square root of pressure of the gas divided by density of the gas. Say the equation number is 4. This is also called the Newton's formula. So we will continue in the next time. Thank you.